Hi, this is the lesson demo for lesson 1.1 part 2. We saw last class that the Malthusian model, which assumes that populations grow at a rate proportional to the size of the population, matches the data well for the US population up until about 1860, and then it begins overestimating. So we need to adjust our assumptions about how populations grow. So our second model for population growth is called the logistic model, and it has two assumptions. Assumption 1 is the Malthusian model's assumption, but we assume that that's only true when the population is small. That if the population is small, the rate of growth of the population is proportional to its size. So as a population gets bigger, it grows faster. We'll assume that's true when the population is small. But if the population gets too large to be supported by its environment and resources, the population will decrease. That is, the rate of growth is negative. So we need to list out what are the variables and parameters here. So we'll have P as population, T will be time. So those are our two main variables. And then parameters are going to be the constant of proportionality for assumption 1. We'll call that K. Okay, and then if the population is too large to be supported by its environment, so there's some critical size of a population where it can be supported by its environment and resources. So I'm going to call that capital C for carrying capacity. Carrying capacity of the environment. So let's remember the logistic model starts out just like the Malthusian model. So it says that the rate of growth of the population, which we denote with a derivative, dp dt, that's the rate of growth of the population, is proportional to the population's size, so equals K times P. So that is assumption 1. And then assumption 2 is that if the population is too large, its rate of growth would have to be negative. So right now, the rate of growth is positive, right? The larger the population, the faster the growth. So right now we have a positive growth rate. So to change it to negative, I could introduce a new factor, multiply by something. Okay, and I want that something to be negative sometimes and positive sometimes. So I want it to be negative when the population is larger than its carrying capacity. So I'm going to compare, one way that I could do that is I could put the population divided by the carrying capacity. And when the population is larger than the carrying capacity, that fraction will be bigger than 1. So if I do 1 minus that, I get the negative factor I'm looking for. When the population is smaller than the carrying capacity, the value of P over C will be less than 1, so 1 minus P over C would be positive. So still positive growth when population is smaller than carrying capacity. If population and carrying capacity are equal, P over C would be 1, and then this whole factor right here would be 0. So if the population equals the carrying capacity, it would not change size. So this is called the logistic model. Rather than giving you the solution to the logistic model, let's think about what the solution functions will look like qualitatively. Okay. So we'll start by looking for equilibrium solutions. Equilibrium solutions are constant functions that satisfy the differential equation. Okay, so if P of t is a constant, that will be my solution. I'm looking for solutions that are constants. So P of t equals a constant. We're looking for that kind of a solution. That means that dp dt is 0, right? The derivative of any constant is 0. So the way we find equilibrium solutions are places where the derivative is 0. So I set my equation Kp times 1 minus P over C equal to 0. So I have two factors, multiply together, you get 0. That means either one factor is 0 or the other factor is 0. So K is a constant of proportionality, so I can just divide both sides by K and I get P of T equals 0. That's one equilibrium solution. And then if I look at my other equation and I want to solve for P, I get 1 equals P over C. Multiply both sides by C, so I get P of T equals C, the carrying capacity. So I have two equilibrium solutions. P of T equals 0. So if your population size is 0, it will stay 0 forever. And if your population size is C, the carrying capacity, it will stay at the carrying capacity forever. So let's continue to think about this a little bit. Like I'm going to draw some qualitative graphs of what other solutions might look like. So here's T, time and population. I know that 0 is an equilibrium solution. So if the population starts at 0, it stays at 0 for all time. I know that C, P of T equals C, is another equilibrium or constant solution. So if the population starts at C, it stays at C for all time. Now, let's say you start somewhere between 0 and C. Given the model, just go look at this model up here. C, the population is smaller than C, right? So this fraction is less than 1. 1 minus something smaller than 1 is just some positive number here. This is a positive number, which means dp dt is positive. Positive times a positive gives a positive. And when the derivative is positive, the function p of t is increasing. So that means that this is going to increase, but it's not going to surpass the carrying capacity. So it would go do something like that. And if we start above the carrying capacity, then P over C is bigger than 1. 1 minus something bigger than 1 is negative. So you have a negative times a positive gives you a negative dp dt, which means that P is decreasing. So it would come down towards the carrying capacity like that. So qualitatively, we see that everything sort of approaches the carrying capacity. So we know quite a lot about the solutions to this differential equation without having to find an analytic solution. However, we'll be able to solve it analytically next class. So next, we're going to adjust our assumptions about how populations grow, again, adding in another important variable. This time, we're going to look at a predator-prey system. So we're going to call the prey rabbits and the predators foxes. And since each population influences the other, we're going to try to model both populations simultaneously. So here are our assumptions. If there are no foxes present, the rabbits reproduce at a rate proportional to their population, and they're not affected by overcrowding. So that's the Malthusian model. In the absence of foxes, rabbits just grow according to the Malthusian model. And then the foxes eat the rabbits, and the rate at which the rabbits are eaten is proportional to the rate at which the foxes and rabbits interact. So the more often they see each other, the more frequently rabbits are eaten. And then without rabbits to eat, the fox population declines at a rate proportional to itself. That is because they would die out without their food source. And the rate at which foxes are born is proportional to the number of rabbits eaten by foxes. So in order for foxes to reproduce, they have to have a food source. And the more often they come into contact with rabbits, the more they get to eat, the more they reproduce. Okay, so let's try to translate these 4 facts into a model. So we're going to have R stand for rabbits, F stand for foxes. And let's just look at the first bullet. When no foxes are present, the rabbits reproduce at a rate proportional to their population. So their reproduction rate, DRDT, is proportional to their population size. So that one's pretty straightforward. And then the foxes eat the rabbits, and the rate at which the rabbits are eaten is proportional to the rate at which the foxes and rabbits interact. Okay, so we need some kind of term that, so first we're going to subtract. The rate is going to decrease. It's going to get smaller as foxes and rabbits interact. So I'm going to subtract something to make the rate get slower when foxes and rabbits interact. So there's several things I could use to model interaction. I need something that shows that when there are more rabbits, interactions will increase. If there are more foxes, interactions will increase. If there's more of both, interactions will increase. So I could add the number of rabbits and foxes together, or I could multiply the number of rabbits and foxes together. Either one will get that effect where if you increase the population of one, the interactions will also increase. And we're just going to make a choice here to use multiplication. It simplifies things later down the road. So I'm going to have R times F be what's called an interaction term. R times F can be used to measure how often rabbits and foxes interact. And then it needs a constant of proportionality, right? Because the rate at which rabbits are eaten is proportional to the rate at which they interact. So I need another constant of proportionality. I think I'll use an alpha. So there's my model for rabbits. And then for foxes, df dt, we know that without rabbits to eat, the fox population declines at a rate proportional to itself. So proportional to its size would be k times f, but it's declining, so it's a negative constant of proportionality. And I've got two k's here, so I'm going to call this one k1 and this one k2. Okay, so their population declines at a rate proportional to its size if they don't have anything to eat. And then my next assumption is the rate at which foxes are born, which would increase the rate of growth of the population, is proportional to the number of rabbits eaten by foxes, which by the second assumption is proportional to the rate at which the foxes and rabbits interact. So for foxes, interaction with rabbits is good, right? It's going to increase the population growth rate. So I'm going to add an interaction term. So when rabbits and foxes interact, that's good for foxes, and the constant of proportionality we can call beta. And we're going to assume that all of these constants, K1, K2, alpha, and beta, are all positive because I used a negative sign here. So that means K2 would have to be positive, and then we put the negative sign in front. So this pair of equations right here, it's called a first order system. It's first order because it only has first derivatives. It's a system of equations because there is more than one. The solution to this first order system is a pair of functions, one for rabbits, one for foxes. Since the two functions depend on each other, you can't just solve one and then the other. You have to solve them simultaneously. And it turns out there's simply no analytic way to do that for most values of the parameters. So we'll have to use a qualitative or a numeric method to study the solutions. One way that we can study the solution numerically is to pick initial values for R and F and use them to calculate values for dr dt and df dt using the given equations. Then you can use the rates of change to estimate new values for R and F a small unit of time later. So let's try it. Let's assume R of 0 is 12, F of 0 is 2, and that all the parameters in the model are 1 just to make things a little bit easier. So my model says dr dt is k times r, but I'm going to take k to be 1, minus alpha rf, and alpha is going to be 1. and df dt is negative f plus rf. And I'm going to calculate dr dt and df dt when r is 12 and f is 2. Okay, so at r equals 12, f equals 2. Calculating both of these. So that tells me that dr dt, the rate at which the rabbit population is growing, is going to be 12 minus 12 times 2, which is negative 12. And my units on dr dt is going to be rabbit units over time units. So rabbits per whatever the time unit is. Let's just call it, I don't know, week. I didn't tell you in the problem, so we'll just make it up. Okay, and then df dt is going to be negative 2 plus 12 times 2, which is 22 foxes per week. So those are the rates of change. So I can use my rate of change. I now know at what speed the rabbit population is declining and at what speed the fox population is increasing. And I can use that to estimate the rabbit population and the fox population 1 week later. So it was at 12, right? R of 0 was 12. That was given. So I had 12 rabbits at time 0. And it is declining. The rabbit population we know is declining by 12 rabbits per week. So if 1 week later, I should have 12 fewer rabbits. So minus 12 is 0 rabbits. And then the fox population, 1 week later, the fox population started with 2 foxes, and I'm adding now 22 foxes per week. So I'm going to add 22, and I now have 24 foxes. 0 rabbits, 24 foxes. Then you can repeat this process. Calculate dr dt and df dt using these 2 new values for r and for f. This will take a very, very long time. It's very tedious. If I wanted to use this process to calculate, say, how many rabbits are there 10 weeks later or 52 weeks later, this is very time intensive. Unless you have a computer program that can do it for you, having a computer do this is very, very helpful and is part of your first project. So we've seen 3 models so far for populations: the Malthusian model, the logistic model, and the predator-prey model. And we've looked at 3 techniques for studying their solutions. Analytic. So far, all we can do is check that a function is a solution, but we'll be able to actually find solutions next class. Qualitative, where we can sketch solutions even though we don't have a formula. And numerical, which is what we just did. The next 3 sections of the text will further illuminate each of those techniques.